not limited to columns that can only be true or false. We can run the where filter on any column by making a logical statement about it. For example, I could ask to keep all the rows where health number is bigger than 50. This is a logical statement, health bigger than 50, because it is either true or false for every row. And of course, the where filter will only keep those rows where this statement evaluates to true. And if I run this, I can see that in all of my results, health will be bigger than 50. And I can also combine smaller logical statements with each other to make more complex logical statements. For example, I could say that I want all the rows where health is bigger than 50 and is alive is equal to true. Now, all of this becomes one big logical statement, and again, this will be true or false for every row, and we will only keep the rows where it is true. And if I run this, you will see that in the resulting table, the health value is always above 50 and is alive is always true. In the next lecture, we will see in detail how these logical statements work and how we can combine them effectively. But now let us focus on the order of operations and how the where statement fits in there. When it comes to the lexical order, the order in which we write things, it is pretty clear from this example. First you have select, then from, and after from you have the where statement. And you have to respect this order. When it comes to the logical order, you can see that the where clause follows right after the from clause. So it is second actually in the logical order. If you think about it, this makes a lot of sense, because the first thing that I need to do is to get the data from where it lives. And then the first thing I want to do after that is that I'm going to drop all the rows that I don't need so that my table becomes actually smaller and easier to deal with. There is no reason why I should carry over rows that I don't actually need, data that I don't actually want, and waste memory and processing power on it, so I want to drop those unneeded rows as soon as possible. And now that you know that where happens at this stage in the logical order, you can avoid many of the pitfalls that happen when you're just learning SQL. Let's see an example. Now take a look at this query. I'm going to the fantasy characters table, and then I'm getting the name and the level. And then I'm defining a new column. This is simply level divided by 10, and I'm calling this level scaled. Now let's say that I wanted to only keep the rows that have at least 3 as level scaled. So I would go here and write a where filter where level scaled bigger than 3. And if I run this, I get an error, unrecognized name. Can you figure out why we get this error? Level scaled is an alias that we assign in the select stage, but the where clause occurs before the select stage, so the where clause has no way to know about this alias. In other words, the where clause is at this point, and our rules say that an operation can only use data produced by operations before it. So the where clause has no way of knowing about the label which is assigned at this stage. So how can we solve this problem right here? The solution is to not use the alias and to instead repeat the logic of the transformation. And this actually works because it turns out that when you write logical statements in the where filter, you can not only reference the columns of the tables, but you can also reference operations on columns. And this way of writing operations on columns and combinations between columns works just as what we have shown in the select part. So that was all you need to know to get started with the where clause, which is a powerful clause that allows us to filter out the rows that we don't need and keep the rows that we need based on logical conditions. Now let's delve a bit deeper into how exactly these logical statements work in SQL. And here is a motivating example for you. This is a selection from the characters table, and we have a where filter, and this where filter is needlessly complicated. And I did this intentionally because by the end of this lecture, you should have no trouble at all interpreting this statement and figuring out for which rows it will be true. And likewise, you will have no problem writing complex statements yourself or deciphering them when you encounter them in the wild. The way that these logical statements work is through something called Boolean algebra, which is an essential theory for working with SQL, but also for working with any other programming language, and is indeed fundamental to the way that computers work. And though the name may sound a bit scary, it is really easy to understand the fundamentals of Boolean algebra. Now, let's look back at so-called normal algebra, meaning the common form that is taught in schools. In this algebra, you have a bunch of elements, which in this case, I'm only showing a few positive numbers, such as 0, 25, 100. You also have operators that act on these elements. For example, the square root symbol, the plus sign, the minus sign, the division sign, or the multiplication sign. And finally, you have operations, right? So in operations, you apply the operators to your elements, and then you get some new elements out of them. So here are two different types of operation. In one case, we take this operator, the square root, and we apply it to a single element. And out of this, we get another element. In the second kind of operation, we use this operator, the plus sign, to actually combine two elements. And again, we get another element in return. Boolean algebra is actually very similar, except that it's simpler in a way because you can only have two elements, either true or false. Those are all the elements that you are working with. And of course, this is why when there's a Boolean field in SQL, it is a column that can only have these two values, which are true and false. Now, just like normal algebra, Boolean algebra has several operators that we can use to transform the elements. And for now, we will only focus on the three most important ones, which are not, and or. And finally, in Boolean algebra, we also have operations. And in operations, we combine operators and elements and get back elements. Now we need to understand how these operators work. So let us start with the not operator. To figure out how a Boolean operator works, we have to look at something that's called a truth table. So let me look up the truth table for the not operator, and in this Wikipedia article, this is available here at logical negation. Now, first of all, we see that logical negation is an operation on one logical value. What does this mean? It means that the not operator works on a single element, such as not true or not false. And this is similar to the square root operator in algebra that works on a single element, a single number. Next, we can see how exactly this works. So, given an element that we call P, and of course P can only be true or false, the negation of P is simply the opposite value. So, not true is false and not false is true. And we can easily test this in our SQL code. So if I say select not true, what do you expect to get? We get false. And if I do select not false, I will of course get true. Next, let's see how the AND operator works. So we've seen that the not operator works on a single element. On the other hand, the AND operator connects two elements, such as writing true and false. And in this sense, the AND operator is more similar to the plus sign here, which is connecting two elements. So what is the result of true and false? To figure this out, we have to go back to our truth tables. And I can see here at the logical conjunction section, which is another word for the AND operator. Now the AND operator combines two elements, and each element can either be true or false. So this creates four combinations that we see here in this table. And what we see here is that only if both elements are true, then the AND operator will return true. In any other case, it will return false. So going back here, if I select true and false, what do you expect to see? I am going to get false. And it's only in the case when I do true and true that the result here will be true. And finally, we can look at the OR operator, which is also known as a logical disjunction. It's also combining two elements. It also has four combinations. But in this case, if at least one of the two elements is true, then you get true. And only if both elements are false, then you get false. And so going back to our SQL, true or true will of course be true. But even if one of them is false, we will still get true. And only if both are false, we will get false. So now you know how the three most important operators in Boolean algebra work. Now, the next step is to be able to solve long and complex expressions such as this one, and you already know how operators work. The only information you're missing is the order of operations. And just like in arithmetic, we have an agreed upon order of operations that helps us solve complex expressions, and the order of operations is written here. First, you solve for not, then you solve for AND, and finally for OR. And as with arithmetic, you first solve for the brackets. So let's see how that works in practice. Let us now simplify this expression. So the first thing I want to do is to deal with the brackets. So if I copy all of this part over here as a comment so it doesn't run as code, you will see that this is the most nested bracket, the innermost bracket in our expression, and we have to solve for this. So what is true or true? This is true, right? And now I can copy the rest of my expression up to here. And here I can solve the innermost bracket as well. So I can say true, and what I have here is false and true. So this is false, right? Because when you have AND, both of them need to be true for it to return true, otherwise it's false. So I will write false. Moving on to the next line, I need to solve what's in the brackets. So I can copy the not, and now I have to solve what's in this bracket over here. Now, there are several operators here, but we have seen that not has the precedence, right? So I will copy true, and here I have not false, which becomes true. And then I can copy the last of the bracket. I'm not gonna do any more at this step to avoid confusion. And then I have or, and I can solve for this bracket over here, and true and false is actually false. Moving on, I can keep working on my bracket, and so I have a lot of operations here, but I need to give precedence to the ands. So the first and that occurs is this one, and that means I have to start with this expression over here. True and true results in true. And then moving on, I will copy the or over here, and now I have another and, which means that I have to isolate this expression. False and true results in false. And finally, I can copy the final and because I'm not able to compute it yet because I needed to compute the left side. And I can copy the remaining part as well. Moving on to the next line, I need to still do the and because the and takes precedence. And so this is the expression that I have to compute. So I will say true or, and then this expression false and true computes to false. And then copy the rest. Now let me make some room over here and go to the next line. And I can finally compute this bracket. We have true or false, which we know is true. Next, I need to invert this value because I have not true, which is false. And then I have or false. And finally, this computes to false. And now for the moment of truth, pun intended, I can run my code and see if the result actually corresponds to what we got. And the result is false. So in short, this is how you can solve complex expressions in Boolean algebra. You just need to understand how these three operators work, and you can use truth tables like this one over here to help you with that. And then you need to remember to respect the order of operations, and then if you proceed step by step, you will have no problem solving this. But now let's go back to the query with which we started, because what we have here is a complex logical statement that is plugged into the where filter, and it isolates only certain rows, and we want to understand exactly how this statement works. So let us apply what we've just learned about Boolean algebra to decipher this statement. Now, what I've done here is to take the first row of our results, which you see here, and just copy the values in a comment. And then I've taken our logical statement and copied it here as well. So let us see what SQL does when it checks for this row. The first thing that we need to do is to take all of these statements in our where filter and convert them to true or false. And to do that, we have to look at our data. Let us start with the first component, which is level bigger than 20. So for the row that we are considering, level is 12. So this comes out as false. Next, I will copy this and here we have isAlive equals true. Now for our row, isAlive equals false, so this statement computes as false. Mentor ID is not null, with null representing absence of data. In our case, mentor ID is 1, so it is indeed not null. So here we have true. And finally, what we have in here is class in Mage Archer. So we have not seen this before, but it should be pretty intuitive. This is a membership test. This is looking at class, which in this case is Hobbit, and checking whether it can be found in this list. And in our case, this is now false. So now that we've plugged in all the values for our row, what we have here is a classic Boolean algebra expression, and we are able to solve this based on what we've learned. So let us go and solve this, and first I need to deal with the brackets, and what I have here, I have an AND and an OR, and the AND takes precedence. So false and false is false, and I will copy the rest, and here I have not false, which is true. Next, we have false or true, which is true, and in the end, this computes to true. Now, in this case, we sort of knew that the result was meant to come out as true because we started from a row that survived the where filter, and that means that for this particular row, this statement had to compute as true. But it's still good to know exactly how SQL has computed this and understand exactly what's going on. And this is how SQL deals with complex logical statements. For each row, it looks at the relevant values in the row so that it can convert the statement to a Boolean algebra expression, and then it uses the Boolean algebra rules to compute a final result, which is either true or false. And then if this computes as true for the row, then the row is kept, and otherwise the row is discarded. And this is great to know because this way of resolving logical statements applies not only to the where component, but to all components in SQL which use logical statements and which we shall see in this course. Let us now look at the distinct clause, which allows me to remove duplicate rows. So let's say that I wanted to examine the class column in my data. So I could simply select it and check out the results. So what if I simply wanted to see all the unique types of class that I have in my data? This is where distinct comes in handy. If I write distinct here, I will see that there are only 4 unique classes in my data. Now, what if I was interested in the combinations between class and guild in my data? So let me remove the distinct from now and add guild here. And for us to better understand the results, I'm going to add an ordering. And here are the combinations of class and guild in my data. There is a character who is an archer and belongs to Gondor, and there are actually 2 characters who are archers and belong to Mirkwood, and there are many hobbits from Shirefolk, and so on. But again, what if I was interested in the unique combinations of class and guild in my data? I could add the distinct keyword here. And as you can see, there are no more repetitions here. Archer and Mirkwood occurs only once. Hobbit and Shirefolk occurs only once because I'm only looking at unique combinations. And of course, I could go on and add more columns and expand the results to show the unique combinations between these columns. So here Hobbit and Shirefolk has expanded again because some hobbits are alive and others unfortunately are not. At the limit, I could have a star here, and what I would get back is actually my whole data, all the 15 rows, because what we're doing here is looking at rows that have the same value on all columns, rows that are complete duplicates, and there are no such rows in the data, So when I do select star, in this case, distinct has no effect. So in short, how distinct works, it looks at the columns that you've selected, only those which you have selected, and then it looks at all the rows, and two rows are duplicate if they have the exact same values on every column that you have selected. And then duplicate rows are removed, and only unique values are preserved. So just like the where filter, the distinct is a clause that removes certain rows, but it is more strict and less flexible in a sense. It only does one job, and that job is to remove duplicate rows based on your selection. And if we look at our map of SQL operations, we can place distinct. It occurs right after select, right? And this makes sense because we have seen that distinct works only on the columns that you have selected. And so it has to wait for select to choose the columns that we're interested in, and then we can deduplicate based on those. For the following lecture on unions, I wanted to have a very clear example. So I decided to go to the characters table and split it in two and create two new tables out of it. And then I thought that I should show you how I'm doing this, because it's a pretty neat thing to know, and it will help you when you are working with SQL in BigQuery. So here's a short primer on yet another way to create a table in BigQuery. You can use your newly acquired power of writing SQL queries to turn those queries into permanent tables. So here's how you can do it. First, I've written a simple query here, and you should have no trouble understanding it by now. Go to the fantasy characters table, keep only rows where isAlive is true, and then get all the columns. Next, we need to choose where the new table will live and how it will be called. So I'm placing it also in the fantasy dataset, and I'm calling it characters alive. And finally, I have a simple command, which is create table. Now, what you see here is a single statement in SQL. It's a single command that will create the table. And you can have, in fact, multiple statements within the same code. And you can run all the statements together when you hit run. The trick is to separate all of them with this semicolon over here. The semicolon tells SQL, hey, this command over here is over, and next I might add another one. So here we have the second statement that we're going to run, and this looks just like the one above, except that our query has changed because we're getting rows where isAlive is false, and then we are calling this table characters dead. So I have my two statements, they're separated by semicolons, and I can just hit run, and I will see over here that BigQuery is showing me the two statements on two different rows, and you can see that they are both done now. So if I open my Explorer over here, I will see that I have two new tables, characters alive and characters dead. And if I go here, for characters alive, isAlive will of course be true on every row. Now, what do you think would happen if I ran this script again? Let's try it. So I get an error. The error says that the table already exists. And this makes sense because I've told SQL to create a table, but SQL says that table already exists. I cannot create it again. So there are ways that we can tell SQL what to do if the table already exists again, so that we specify the behavior we want and we are not going to just get an error. One way is to say create or replace table, fantasy characters alive. And what this will do is that if the table already exists, BigQuery will delete it and then create it again. Or in other words, it will overwrite the data. So let's write it down too, and let's make sure that this query actually works. So when I run this, I will get no errors, even if the table already existed, because BigQuery was able to remove the previous table and create a new one. Alternatively, we may want to create the table only if it doesn't exist yet and leave it untouched otherwise. So in that case, we could say create table if not exists. So what this will do is that if this table is already existing, BigQuery won't touch it and it won't throw an error, but if it doesn't exist, it will create it. So let us write it down too, and make sure that this query runs without errors. And we see that also here we get no errors. And that, in short, is how you can save the results of your queries in BigQuery and make them into full-fledged tables that you can save and query at will. And I think this is a really useful feature if you're analyzing data in BigQuery, because any results of your queries that you would like to keep, you can just save them and then come back and find them later. Let's learn about unions. Now, to show you how this works, I have taken our characters table and I have split it into two parts. And I believe the name is quite self-descriptive. There is a separate table now for characters who are alive and a separate table for characters who are dead. And you can look at the previous lecture to see how I've done this, how I've used a query to create two new tables. But this is exactly the characters table with, the same schema, the same columns, the same times. It's just split in two based on the is alive column. Now let us imagine that we do not have the fantasy.characters table anymore. We do not have the table with all the characters because it was deleted or we never had it in the first place. And let's pretend that we only have these two tables now, characters alive and characters dead. And we want to reconstruct the characters table out of it. We want to create a table with all the characters. How can we do that? Now what I have here are two simple queries: select star from fantasy characters alive and select star from fantasy characters dead. So these are two separate queries, but actually in BigQuery there are ways to run multiple queries at the same time. So I'm gonna show you first how to do that. Now an easy way to do that is to write your queries and then add a semicolon at the end. And so what you have here is basically a SQL script which contains multiple SQL statements, in this case two, and if you hit run, all of these will be executed sequentially. And when you look at the results, so you're not just getting a table anymore because it's not just a single query that has been executed, but you can see that there have been two commands that have been executed, which are here. And then for each of those two, you can simply click view results and you will get to the familiar results tab for that. And if I want to see the other one, I will click on the back arrow here and click on the other view results, and then I can see the other one. Another way to handle this is that I can select the query that I'm interested in and then click run, and here I see the results. So BigQuery has only executed the part that I have selected. Or I can decide to run the other query in my script, select it, click run, and then I will see the results for that query. And this is a pretty handy functionality in BigQuery. It's also functionality that might give you some headaches if you don't know about it, because if for some reason you selected a part of the code during your work and then you just want to run everything, you might hit run and get an error here because BigQuery is only seeing the part that you selected and cannot make sense of it. So it's good to know about this. But our problem has not been solved yet, because remember, we want to reconstruct the characters table, and what we have here are two queries, and we can run them separately and we can look at the results separately, but we still don't have a single table with all the results. And this is where union comes into play. Union allows me to stack the results from these two tables. So if I first I will take off the semicolons, because this will become a single statement. And then in between these two queries, I will write union distinct. And when I run this, you can verify for yourself, we have 15 rows and we have indeed reconstructed the characters table. So what exactly is going on here? Well, it's actually pretty simple. SQL is taking all of the rows from this first query, and then all of the rows for the second query, and then it's stacking them on top of each other. So you can really imagine the act of horizontally stacking a table on top of the other to create a new table which contains all of the rows of these two queries combined. And that, in short, is what union does. Now, there are a few details that we need to know when working with union. And to figure them out, let us look at a toy example. So I've created two very simple tables, toy1 and toy2, and you can see how they look in these comments over here. They all have three columns, which are called imaginatively col1, col2, col3, and then this is the toy1 table, and then this is the toy2 table. Now, just like before, we can combine these tables by selecting all of them and then writing a union in between them. Now, in BigQuery, you're not allowed to write union without a further qualifier, a keyword, and it has to be either all or distinct. So you have to choose one of these two. And what is the choice about? Well, if you do union all, you will get all of the rows that are in the first table and those that are in the second table, regardless of whether they are duplicate. Okay? But with union distinct, you will get, again, all of the rows from the two tables, but you will only consider unique rows. You will not get any duplicates. Now we can see that these two tables share a column which is actually identical. One true yes over here and the same row over here. Now, if I write union all, I expect the result to include this row twice. So let us verify that. And you can see that here you have one true yes, and at the end you also have one true yes. And in total you get 4 rows, which are all the rows in the two tables. However, if I do union distinct, I expect to get 3 rows, and I expect this row to appear only once and not to be duplicated. Again, you need to make sure you're not selecting any little part of your script before you run it, so the whole script will be run. And as you can see, we have 3 rows and there are no duplicates. Now, it's interesting that BigQuery actually forces you to choose between all or distinct, because in many SQL systems, for your information, you are able to write union without any qualifier, and in that case, it means union distinct. So in other SQL systems, when you write union, it is understood that you want union distinct. And if you actually want to keep the duplicate rows, you will explicitly write union all. But in BigQuery, you always have to explicitly say whether you want union all or union distinct. Now, the reason this command is called union and not like stack or something else is that this is a set terminology, right? This comes from the mathematical theory of sets, which you might remember from school, and the idea is that a table is simply a set of rows. So this table over here is a set of 2 rows, and this table over here is a set of two rows. And once you have two sets, you can do various set operations between them. And the most common operation that we do in SQL is unioning, and unioning means combining the values of two sets. So you might remember from school the Venn diagram, which is a typical way to visualize the relations between sets. So in this simple Venn diagram, we have two circles A and B, which represent two sets. And in our case, A represents the collection of rows in the first table, and B represents all the rows that are in the second table. So what does it mean to union these sets? It means taking all of the elements that are in both sets. So taking all of the rows that are in both tables. And what is the difference here between union distinct and union all? Where you can see that the rows of A are this part over here plus this part over here, and the rows of B are this part over here plus this part over here. And so when we combine them, we're actually counting the intersection twice. We're counting this part twice. And so what do you do with this double counting? Do you keep it or do you discard it? If you do union all, you will keep it. So rows that are in common between A and B will duplicate. You will see them twice. But if you do union distinct, you will discard it. And so you won't have any duplicates in the results. So that's one way to think about it in terms of sets. But we also know that union is not the only set operation, right? There are other set operations. A very popular one is the intersect operation. Now the intersect looks like this, right? It says take only the elements that are in common between these two sets. So can we do that in SQL? Can we say, give me only the rows that are in common between the two tables? And the answer is yes, we can do this. And if we go back here, we can, instead of union, write intersect and then distinct. And what do you expect to see after I run this command? Take a minute to think about it. So what I expect to see is to get only the rows that are shared between the two tables. Now there is one row which is shared between these two tables, which is the one true yes row, which we have seen. And if I run this, I will get exactly this row. So intersect distinct gives me the rows that are shared between the two tables, and I have to write intersect distinct. I cannot write intersect all because actually it doesn't mean anything, so it's not going to work. And here's another set operation which you might consider, which is subtraction. So what if I told you, give me all of the elements in A except the elements that A shares with B? So what would that look on the drawing? It would look like this, right? So this is taking all of the elements that are in A except these ones over here because they are in A, but they're also in B, and I don't want the elements shared with B. And yes, I can also do that in SQL. I can come here and I could say, give me everything from toy 1 except distinct everything from toy 2. And what this means is that I want to get all of my rows from toy 1 except the rows that are shared with toy 2. So what do you expect to see when I run this? Let's hit run. And I expect to see only this row over here because this other row is actually shared with B. And this is what I get. Again, you have to write except distinct. You cannot write except all because it actually doesn't mean anything. And keep in mind that unlike the previous two operations, which are union and distinct, the except operation is not symmetric, right? So if I swap the tables over here, I actually expect to get a different result, right? I expect to see this row over here selected because I'm saying, give me everything from this table, toy 2, except the rows that are shared with toy 1. So let us run this and make sure. And in fact, I get the 3 true maybe row. So careful that the except operation is not symmetric. The order in which you put the two tables matters. So that was a short overview of union, intersect, except, and I will link this here, which is the BigQuery documentation on this, and you can see that they're actually called set operators. In fact, in real life, you almost always see union. Very rarely you will see somebody using intersect or except. A lot of people also don't know about them. But I think it's worth it that we briefly looked at all three, and it's especially good for you to get used to thinking about tables as sets of rows and thinking about SQL operations in terms of set operations, and that will also come in handy when we study joins. But let us quickly go back to our toy example, and there are two essential prerequisites for you to be able to do a union or any type of sort operations. Number one, the tables must have the same number of columns. And number two, the columns must have the same data type. So as you can see here, we are combining toy 2 and toy 1, and both of them have 3 columns, and the first column is an integer, the second is a boolean, and the third is a string in both tables, and this is how we are able to combine them. So what would happen if I went to the first table and I got only the first 2 columns and then I tried to combine it? You guessed it, I would get an error because I have a mismatched column count. So if I want to select only the first 2 columns in a table, I need to select only the first 2 columns in another table. And then the union will work. Now what would happen if I messed up the order of the columns? So let's say that here I will select column 1 and column 3, and here I will select column 1 and column 2. Let me run this, and I will get an error because of incompatible types, string and bool. So what's happening here is that SQL is trying to get the values of col 3 over here and put it into col 2 over here. And it's trying to get a string and put it into a boolean column. And that simply doesn't work because, as you know, SQL enforces strict types on columns. And so this will not work. But of course, I could select col 3 in here as well. And now again, we will have a string column going into a string column. And of course, this will work. So to summarize, you can union or intersect or accept any 2 tables as long as they have the same number of columns and the columns have the same data types. Let us now illustrate a union with a more concrete example. So we have our items table here and our characters table here. So the items table represents like magical items, right? While the characters table, we're familiar with it, represents actual characters. So let's say that you are managing a video game and someone asks you for a single table that contains all of the entities in that video game, right? And the entities include both characters and items. So you want to create a table which combines these 2 tables into one. We know we can use union to do that. We know we can use union to stack all the rows. But we cannot directly union these 2 tables because they have a different schema, right? They have a different number of columns, and then those columns have different data types. But let's analyze what these two tables have in common and how we could maybe combine that. So first of all, they both have an ID, and in both cases it's an integer. So that's already pretty good. They both have a name, and in both cases the name is a string. So we can combine that as well. The item type can be thought of being similar to the class, and then each item has a level of power, which is expressed as an integer, and each character has a level of experience, which is expressed as an integer, and you can think that they are kind of similar. And then finally, we have a timestamp field representing a moment in time for both columns, which are date added and last active. So looking at these columns that the two have sort of in common, we can find a way to combine them. And here's how we can translate these into SQL, right? So I went to the fantasy items table and I selected the columns that I wanted. And then I went to the characters table and I selected the columns that I wanted to combine with those in the right order. So we have ID with ID, name with name, class with item type, level with power, and last active with date added. So I have my columns, they're in the right order. I wrote union distinct, and if I run this, you will see that I have successfully combined the rows from these two tables by finding out which columns they have in common, and then writing them in the right order and then adding union distinct. Now all the columns that we've chosen for the combination have the same type. But what would happen if I wanted to combine two columns that are not actually the same type? So let's say, what if we wanted to combine rarity, which is a string, with experience, which is an integer? As you know, I cannot do this directly, but I can go around it by either taking rarity and turning it into an integer, or taking experience and turning it into a string. I just have to make sure that they both have the same data type. Now, the easiest way is usually to take any other data type and turn it into a string, because you just turn it into text. So let's say that for the sake of this demonstration, we will take integer experience, which is an integer, and turn it into a string, which is text, and then combine that with rarity. So I will go back to my code and I will make some room over here. And here in items, I will add rarity. And here in characters, I will add experience. And you can see that I already get an error here saying that the union distinct has incompatible types, just like expected. So what I want to do here is to take experience and turn it into string, and I can do that with the cast function. So I can do cast experience as string, and what this will do is basically take these values and convert them to string. And if I run this, you can see that this has worked. So we combined two tables into one, and now the result is a single table. It has a column called rarity. The reason it's called rarity is that it's taking the name from the first table in the operation, but we could of course rename it to whatever we need. And this is now a text column because we have combined a text column with also a text column thanks to the casting function. So what we see here are a bunch of numbers which came originally from the experience column from the characters table, but they're now converted to text. And if I scroll down, then I will also see the original values of rarity from the items table. Finally, let us examine union in the context of the logical order of SQL operations. So you can see here that we have our logical map, but it looks a bit different than usual. And the reason it's different is that we are considering what happens when you union two tables. And here the blue represents one table and the red represents the other table. So I wanted to show you that all of the ordering that we have seen until now, so first get the table, then use the filter with where, then select the columns you want, and if you want, use distinct to remove duplicates. All of this happens in the same order, separately for the two tables that you are unioning. And this applies to all of the other operations like joining and grouping, which we will see later in the course. So at first, the two tables are working on two separate tracks, and SQL is doing all these operations on them in this specific order. And only at the end of all this, only after all of these operations have run, then we have the union. And in the union, these two tables are combined into one. And only after that, only after the tables have been combined into one, you apply the last two operations, which are order by and limit. And actually, nothing forces you to combine only two tables. You could actually have any number of tables that you are combining in union, but then the logic doesn't change at all. All of these operations will happen separately for each of the tables, and then only when all of these operations are done, only when all of the tables are ready, then they will be combined into one. And if you think about it, it makes a lot of sense because first of all, you need the select to have run in order to know what is the schema of the tables that you are combining. And then you also need to know if distinct has run on each table because you need to know which rows you need to combine in the union. And that is all you need to know to get started with union, this very powerful statement that allows us to combine rows from different tables. Let us now look at order by. So I'm looking at the characters table here, and as you can see, we have an ID column that goes from 1 to 15, which assigns an ID to every character, but you will see that the IDs don't appear in any particular order. And in fact, this is a general rule for SQL. There is absolutely no order guarantee for your data. Your data is not stored in any specific order, and your data is not going to be returned in any specific order. And the reason for this is fundamentally one of efficiency, because if we had to always make sure that our data was perfectly ordered, that would add a lot of work. It would add a lot of overhead to the engine that makes the queries work, and there's really no reason to do this. However, we do often want to order our data when we are querying it. We want to order the way that it is displayed, and this is why the order by clause is here. So let us see how it works. I am selecting everything from fantasy characters, and again, I'm going to get the results in no particular order, but let's say I wanted to see them in order by name, so then I would do order by name. And as you can see, the rows are now ordered alphabetically according to the name. I could also invert the order by writing desc, which stands for descending, and that means descending alphabetical order, which means from the last letter in the alphabet to the first. I can of course also order by number columns such as level, and we would see that the level is increasing here. And of course that could also be descending to go in the opposite direction. And the corresponding keyword here is ask, which stands for ascending, and this is actually the default behavior, so even if you omit this, you will get the same, going from the smallest to the largest. I can also order by multiple columns, so I could say order by class and then level. And what that looks like is that, first of all, the rows are ordered by class. So as you can see, this is done alphabetically. So first archer, and then the last is warrior. And then within each class, the values within the class are ordered according to the level, going from the smallest level to the biggest level. And I can invert the order of one of them, for example, class. And in this case, we will start with warriors. And then within the warrior class, we will still order the level in ascending order. So for every column that's in the ordering, I can decide whether that ordering is in ascending order or descending order. Now let us remove this and select the name and the class. And once again, I get my rows in no particular order, and I'm seeing the name and the class. So I wanted to show you that you can also order by columns which you have not selected. So I could order these elements by level, even though I'm not looking at level, and it will work all the same. And finally, I can also order by operations. So I could say take level divided by experience and then multiply that by 2 for some reason. And it would also work in the ordering. Even though I am not seeing that calculation is being done in the background and used for the ordering. So I could actually take this here and copy it, create a new column, call it calc for calculation. And if I show you this, you will see the results are not very meaningful, but you will see that they are in ascending order. So we have ordered by that. And sometimes you will see this notation over here, order by 2, 1, for example. And as you can see, what we've done here is that we've ordered by class, first of all, because we starting with archers and going to warriors. And then within each class, we are ordering by name, also in ascending order. So this is basically referring to the columns that are referenced in the select. 2 means order by the second column, which you have referenced, which in this case is class. And 1 means order by the first column that you referenced. So it's basically a shortcut that people sometimes use to avoid rewriting the names of columns that they have selected. And finally, when we go back to the order of operations, we can see that order by is happening really at the end of all of this process. So as you will recall, I have created this diagram that's a bit more complex to show what happens when we union different tables together. What happens is that basically all these operations, they run independently on each table, and then finally the tables get unioned together. And after all of this is done, SQL knows the final list of rows that we will include in our results. And that's the right moment to order those rows. It would not be possible to do that before, so it makes sense that order is located here. Let us now look at the limit clause. So what I have here is a simple query. It goes to the characters table, it filters for the rows where the character is alive, and then it gets 3 columns out of this. So let's run this query, and you can see that this query returns 11 rows. Now let us say that I only wanted to see 5 of those rows, and this is where limit comes into place. Limit will look at the final results and then pick 5 rows out of those results, reducing the size of my output. And here you can see that we get 5 rows. Now, as we said in the lecture of ordering, by default, there is no guarantee of order in a SQL system. So when you are getting all your data with a query and then you run limit 5 on top of it, you have no way of knowing which of the rows will be selected to fit amongst those 5. You're basically saying that you're okay with getting any 5 of all of the rows from your result. Because of this, people often will use limit in combination with order by. For example, I could say order by level and then limit 5. And what I would get here is essentially the first 5 most inexperienced characters in my dataset. And let us say that you have a problem of finding the least experienced character in your data. the character with the lowest level. So of course you could say order by level and then limit 1, and you would get the character with the lowest level, right? And this works. However, it is not ideal. There is a problem with this solution. So can you figure out what the problem with this solution is? The problem will be obvious once I go back to limit 5 and I look here and I see that I actually have two characters which have the lowest level in my dataset. So in theory, I should be able to return both of them because they both have the lowest level. However, when I write limit 1, it simply cuts the rows in my output and it is unaware of that further information that is here in this second row. And in the further lectures, we will see how we can solve this better and get results which are more precise. And if we look at the logical order of operations, we can see that limit is the very last operation. And so all of the logic of our query is executed, all our data is computed, and then based on that final result, we sometimes decide to not output all of it, but to output a limited number of rows. So a common mistake for someone who is starting with SQL is thinking that they can use limit in order to have a cheaper query. For example, you could say, oh, this is a really large table. This table has 2 terabytes of data. It would cost a lot to scan the whole table. So I will say select star, but then I will put limit 20 because I only want to see the first 20 rows. And that means that I will only scan 20 rows and my query will be very cheap, right? No, that is actually wrong. That doesn't save you anything. And you can understand this if you look at the map, because all of the logic is going to execute before you get to limit. So you're going to scan the whole table when you say select star, and you're gonna apply all of the logic, and the limit is actually just changing the way your result is displayed. It's not actually changing the way your result is computed. If you did want to write your query so that it scans less rows, one thing you should do is focus on the where statement actually, because the where statement is the one that runs in the beginning, right after getting the table, and it is able to actually eliminate rows, which usually saves you on computation and money and so on. However, I do need to say that there are systems where writing limit may actually turn into savings, because different systems are optimized in different ways and allow you to do different things with the commands. But as a rule, usually with SQL, limit is just changing the way your result is displayed and doesn't actually change anything in the logic of execution. Let us now look at the case clause, which allows us to apply conditional logic in SQL. So you can see here a simple query. I am getting the data from the characters table. I am filtering it so that we only look at characters who are alive. And then for each character, we're getting the name and the level. Now, when you have a column that contains numbers such as level, one typical thing that you do in data analysis is bucketing. And bucketing basically means that I look at all these multiple values that level can have and I reduce them to a smaller number of values so that whoever looks at the data can make sense of it more easily. Now, the simplest form of bucketing that you can have is the one that has only 2 buckets, right? So looking at level, our 2 buckets, for example, could be in one bucket we'd put values that are equal or bigger than 20, so characters who have a level that's at least 20, and in the other bucket we put all the characters that have a level that is less than 20, for example. Now, how could I define those 2 buckets? So we know that we can define new columns in the select statement and that we can use calculations and logical statements to define those columns. So one thing that I could do would be to go here and then write level bigger or equal than 20. And then call this new column level at least 20, for example. And when I run this, I get my column. Now, of course, this is a logical statement, and for each row, this will be true or false. And then you can see that our new column here gives us true or false on every column. And this is a really basic form of bucketing because it allows us to take, level has basically 11 different values in our data, and it can be complicated to look at this many values at once. And now we've taken these 11 values and reduced them to two buckets so that we have organized our data better and it's easier to read. But there are two limitations with this approach. One, I might not want to call my buckets true or false. I might want to give more informative names to my buckets, such as experienced or inexperienced, for example. The other limitation is that with this approach, I can effectively only divide my data in two buckets, because once I write a logical statement, it's either true or false, so my data gets divided in two. But often it's the case that I want to use multiple buckets for my use case. Now, bucketing is a typical use case for the case when statement, so let's see it in action now. So let me first write a comment, not any actual code, where I define what I want to do, and then I will do it with the code. So I have written here the buckets that I want to use to classify the character's level. So up to 15, they are considered low experience. Between 15 and 25, they are considered mid, and anything above 25, we will classify as super. Now let us apply the case clause to make this work. So the case clause is always bookended by these two parts, case and end. So it starts with case, it ends with end, and a typical error when you're getting started is to forget about the end part. So my recommendation is to always start by writing both of these and then going in the middle to write the rest. Now in the middle, we're going to define all the conditions that we're interested in, and each condition starts with the keyword when and is then followed by a logical condition. So our logical condition here is level smaller than 15. Now we have to define what to do when this condition is true, and it follows with the keyword then. And when this condition is true, we want to return the value low, which is a string, a piece of text that says low. Next, we proceed with the following condition. So when level is bigger and equal to 15 and level is lower than 25. So if you have trouble understanding this logical statement, I suggest you go back to the lecture about Boolean algebra. But what we have here, there are two microstatements, right? Level under 25 and level equal or bigger than 15. They are connected by and, which means that both of these statements have to be true in order for the whole statement to be true, which is what we want in this case, right? And what do we want to return in this case? We will return the value mid. And the last condition that we want to apply, when level is bigger or equal than 25, then we will return super. Now, all of this that you see here, this is the case clause, right? Or the case statement. And all of this is basically defining a new column in my table. And given that it's a new column, I can use the aliasing to also give it a name. And I can call this level bucket. Now let's run this and see what we get. And as you can see, we have our level bucket, and the characters that are above 25 are super, and then we have a few mids, and then everyone who's under 15 is low. So we got the results we wanted, and now let us see exactly how the case statement works. So I'm going to take Gandalf over here, and he has level 30. So I'm going to write over here level equals 30 because we're looking at the first row, and that is the value of level. And then I'm going to take the conditions for the case statement that we are examining and add them here as a comment. Now, because in our first row level equals 30, I'm going to take the value and substitute it here for level. Now what we have here is a sequence of logical statements, and we have seen how to work with these logical statements in the lecture on Boolean algebra. Now our job is to go through each of these logical statements in turn and evaluate them, and then as soon as we find one that's true, we will stop. So the first one is 30 smaller than 15. Now this is false, so we continue. The second one is a more complex statement. We have 30 greater or equal to 15, which is actually true, and 30, oops, I did not substitute it there, but I will do it now, and 30 smaller than 25, which is false. And we know from our Boolean algebra that true and false evaluates to false. Therefore, the second statement is also false, so we continue. And now we have 30 greater or equal than 25, which is true, so we finally found a line which evaluates as true, and that means that we return the value super. And as you can see for Gandalf, we have indeed gotten the value super. Let us look very quickly at one more example. We get Legolas, which is level 22. And so I will once again copy this whole thing and comment it. And I will substitute 22 for every value of level, because that's the row we're looking at. And then looking at the first row, 22 smaller than 15 is false, so we proceed. And then looking at the second row, 22 bigger than 15 is true, and 22 smaller than 25 is also true, so we get true and true, which evaluates to true, and so we return mid. And then looking at Legolas, we get mid. So this is how the case when statement works in short. For each row, you insert the values that correspond to your row, in this case, the value of level, and then you evaluate each of these logical conditions in turn, and as soon as one of them returns true, then you return the value that corresponds to that condition, and then you move on to the next row. Now I will clean this up a bit. And now looking at this statement now and knowing what we know about the way it works, can we think of a way to optimize it, to make it nicer, to remove redundancies? Think about it for a minute. Now, one thing we could do to improve it is to remove this little bit over here, because if you think about it, this part that I've highlighted is making sure that the character is not under 15, so that it can be classified as mid. But actually, we already have the first condition that makes sure that if the character is under 15, then the statement will output low and then move on. So if the character is under 15, we will never end up in the second statement. But if we do end up in the second statement, we already know that the character is not under 15. This is due to the fact that case when proceeds condition by condition and exits as soon as the condition is true. So effectively, I can remove this part over here, and then at the second condition, only make sure that the level is below 25, and you will see if you run this that our bucketing system works just the same. And the other improvement that I can add is to replace this last line with an else clause. So the else clause takes care of all the cases that did not meet any of the conditions that we specified. So the case statement will go condition by condition and look for a condition that's true, but in the end, if none of the conditions were true, it will return what the else clause says. So it's like a fallback for the cases when none of our conditions turned out to be true. And if you look at our logic, you will see that if this has returned false and this has returned false, all that's left is characters that have a level which is either 25 or bigger than 25. So it is sufficient to use an else and to call those super. And if I run this, you will see that our bucketing works just the same. For example, Gandalf is still marked as super because in the case of Gandalf, this condition has returned false and this condition has returned false, and so the else output has been written there. Now, what do you think would happen if I completely removed the else? What do you think would happen if I only had two conditions, but it can be the case that none of them is true? What will SQL do in that case? Let us try it and see what happens. So the typical response in SQL when it doesn't know what to do is to select a null value, right? And if you think about it, it makes sense because we have specified what happens when level is below 15 and when level is below 25, but none of these are true and we haven't specified what we want to do when none of these are true. And because we have been silent on this issue, SQL has no choice but to put a null value in there. So this is practically equivalent to saying else null. This is the default behavior for SQL when you don't specify an else clause. Now, like every other piece of SQL, the case statement is quite flexible. For instance, you are not forced to always create a text column out of it. You can also create an integer column, so you could define a simpler leveling system for your characters by using 1 and 2, else 3 for the higher level characters. And this of course will also work, as you can see here. However, one thing that you cannot do is to mix types, right? Because what this does is that it results in one column, in a new column. And as you know, in SQL, you are not allowed to mix types between columns. So always keep it consistent when it comes to typing. And then when it comes to writing the when condition, all the computational power of SQL is available. So you can reference columns that you are not selecting. You can run calculations as I am doing here, and you can chain logical statements, right? Boolean statements in complex ways. You can really do anything you want. Although I generally suggest to keep it as simple as possible for your sake and the sake of the people who use your code. And that is really all you need to know to get started with the case statement. To summarize, the case statement allows us to define a new columns whose values are changing conditional on the other values of my row. This is also called conditional logic, which means that we consider several conditions and then we do have different behaviors based on which condition is true. And the way it works is that in the select statement, when you are mentioning all your columns, you create a new column, which in our case is this one, and you bookend it with a case and an and. And then between those, you write your actual conditions. So every condition starts with a when, is followed by a logical statement, which needs to evaluate to true or false, and then has the keyword then, and then a value. And then the case when statement will go through each of these conditions in turn, and as soon as one of them evaluates to true, it will output the value that you have specified. If none of the conditions evaluate to true, then it will output the value that you specify in the else keyword, and if the else keyword is missing, it will output null. And so this is what you need to use the case statement, and then experience and exercise and coding challenges will teach you when it's the case to use it, pun intended. Now, where does the case statement fit in our logical order of SQL operations? And the short answer is that it is defined here at the step when you are selecting your columns. That's when you can use the case when statement to create a new column that applies your conditional logic. And this is the same as what we've shown in the lecture on SQL calculations. You can use select statement not only to get columns which already exist, but to define new columns based on calculations and logic. Now, let us talk about aggregations, which are really a staple of any sort of data analysis. And an aggregation is a function that takes any number of values and compresses them down to a single informative value. So I'm looking here at my usual characters table, but this is the version that I have in Google Sheets. And as you know, we have this level column, which contains the level of each character. And if I select this column in Google Sheets, you will see that in the bottom right corner, I can see here a number of aggregations on this column. And like I said, no matter how many values there are in the level columns, I can use aggregations to compress them to one value. And here you see some of the most important aggregations that you will work with. Sum, simply adding up all values together. The average, which is doing the sum and then dividing by the number of values. The minimum value, the maximum, the count, and the count numbers, which is the same here. So these are basically summaries of my column, and you can imagine in cases where you have thousands or millions of values, how useful these aggregations can be for you to understand your data. Now here's how I can get the exact same result in SQL. I simply need to use the functions that SQL provides for this purpose. So as you can see here, I'm asking for the sum, average, minimum, maximum, and count of the column level. And you can see the same results down here. Now, of course, I could also give names to this column. For example, I could take this one and call it max level. And in the result, I will get a more informative column name, and I can do the same for all columns. Now, of course, I can run aggregations on any columns that I want. For example, I could also get the maximum of experience and call this max experience. And I can also run aggregations on calculations that involve multiple columns as well as constants. So everything we've seen about applying arithmetic and logic in SQL also applies. Now, of course, looking at the characters table, we know that our columns have different data types, and the behavior of the aggregate functions also is sensitive to the data types of the columns. For example, let us look at the many text columns that we have, such as class. Now, clearly not all of the aggregate functions that we've seen will work on class, because how would you take the average of these values? It's not possible, right? However, there are some aggregate functions that also work on strings. So here's an example of aggregate functions that we can run on a string column such as class. First we have count, which simply counts the total number of non-null values. And I will give you a bit more detail about the count functions soon. Then we have minimum and maximum. Now, the way that strings are ordered in SQL is something called lexicographic order, which is basically a fancy word for alphabetical order. And basically you can see here that for minimum we get the text value that occurs earlier in alphabetical order, whereas warrior occurs last. And finally, here's an interesting one called string ag. And what this does is that this is a function that actually takes two arguments. The first argument, as usual, is the name of the column, and the second argument is a separator. And what this outputs is now a single string, a single piece of text, where all of the other pieces of text have been glued together and then separated by this character that we specified over here, which in our case is a comma. Now, if you go to the Google documentation, you will find an extensive list of all the aggregate functions that you can use in Google SQL. And this includes the ones that we've just seen, such as average or max, as well as a few others that we will not explore in detail here. So let us select one of them, such as average, and see what the description looks like. Now you can see that this function returns the average of all values that are not null, and don't worry about this expression in an aggregated group. For now, just think about this as meaning all the values that you provide to the function, all the values in the column. Now, there is a bit about window functions, which we will see later. And here there are, in the caveat section, there are some interesting edge cases. For example, what happens if you use average on an empty group, or if all values are null? In that case, it returns null, and so on. You could see what the function does when it finds these edge cases. And here is perhaps the most important section, which is supported argument types. And this tells you what type of columns you can use this aggregation function on. So you can see that you can use average on any numeric input type, right? Any column that contains some kind of number, and also on interval. An interval, we haven't examined it in detail, but this is actually a data type that specifies a certain span of time. So interval could express something like 2 hours or 4 days or 3 months. It is a quantity of time. And finally, in this table, returned data types, you can see what the average function will give you based on the data type that you insert. So if you insert an integer column, it will return to you a float column. And that makes sense because the average function involves a division, and that division will usually give you floating point values. But for any other of the allowed input types, such as numeric, bit numeric, and so on, and these are all data types which represent numbers in BigQuery, the average function, as you can see here, will preserve that data type. And finally, we have some examples. So whenever you need to use an aggregate function, that is, whenever you need to take many values, a sequence of multiple values, and compress them all down to one value, but you're not sure about which function to use or what the behavior of the function is, you can come to this page and look up the functions that interest you and then read the documentation to see how they work. Now here's an error that typically occurs when starting out with aggregations. So you might say, Well, I want to get the name of each character and their level, but I also want to see the average of all levels, and because I want to compare those two values. I want to compare the level of my character with the average on all levels. So I can write a query that looks like this, right? Go to the fantasy characters table and then select name, level, and then average level. But as you can already see, this query is not functioning, it's giving me an error, and the error says that the select list expression references column name, which is neither grouped nor aggregated. So what does this actually mean? To show you what this means, I've gone back to my Google Sheets where I have the same data for my characters table, and I have copy pasted our query over here. Now, what this query does, it takes the name column, so I will copy paste it over here, and then it takes the level column, copy paste this here as well, and then it computes the average over level. Now I can easily compute this with sheet formula by writing equal and then calling the function, which is actually called average. And then within the function, I can select all these values over here and I get the average. Now, this is the result that SQL computes, but SQL is actually not able to return this result. And the reason is that there are 3 columns, but they have mismatching number of values. Specifically, these 2 columns have 15 values each, whereas this column has a single value. And SQL is not able to handle this mismatch. Because, as a rule, every SQL query needs to return a table. And a table is a series of columns where each column has the same number of values. If that constraint is not respected, you will get an error in SQL. And we will come back to this limitation when we examine advanced aggregation techniques. But for now, just remember that you can mix non-aggregated columns with other non-aggregated columns, such as name and level, and you can mix aggregated columns with aggregated columns, such as average level with sum level, for example. So I could simply do this, and I would be able to return this as a table, because as you can see, there are 2 columns, both columns have a single row, the number of rows matches, and this is actually valid. But you might ask, can't I simply take this value over here and just copy it in every row, and until I make sure that average level has the same number of values as name and level, and so return a table and respect that constraint? Indeed, this is possible. You can totally do this, and then it would work, and then this whole table would become a single table and you would be able to return this result. However, this requires the use of window functions, which is a feature that we will see in later lectures. But yes, it is totally possible and it does solve the problem. Now, here's a special aggregation expression that you should know about because it is often used, which is the count star. And count star is simply counting the total number of rows in a table. And as you can see, if I say from fantasy characters select count star, I get the total count of rows in my results. And this is a common expression used across all SQL systems to figure out how many rows a table has. And of course, you can also combine it with filters with the where clause in order to get other types of measures. For example, I could say where is alive equals true, and then the count would become actually the count of characters who are alive in my data. So this is a universal way to count rows in SQL, although you should know that if you're simply interested in the total rows of a table and you are working with BigQuery, an easy and totally free way to do it is to go to the Details tab and look at the number of rows here. So this was all I wanted to tell you about simple aggregations for now. And last question is, why do we call them simple? Simple as opposed to what? I call them simple because the way we've seen them until now, the aggregations take all of the values of a column and simply return one summary value. For example, the sum aggregation will take all of the values of the level column and then return a single number, which is the sum of all levels. And more advanced aggregations involved grouping our data. For example, a question we might ask is, what is the average level for mages as opposed to the average level for archers and for hobbits and for warriors and so on? So now you're computing aggregations not over your whole data, but over groups that you find in your data. And we will see how to do that in the lecture on GroupBy. But for now, you can already find out a lot of interesting stuff about your data by running simple aggregations. Let us now look at subqueries and common table expressions. And these are two fundamental functionalities in SQL. These functionalities solve a very specific problem. And the problem is the following. Sometimes you just cannot get the result you require with a single query. Sometimes you have to combine multiple SQL queries to get where you need to go. So here's a fun problem that will illustrate my point. So we're looking at the characters table and we have this requirement. We want to find all those characters whose experience is between the minimum and the maximum value of our experience. Another way to say this, we want characters who are more experienced than the least experienced character, but less experienced than the most experienced character. In other words, we want to find that middle ground that is between the least and the most experienced characters. So let us see how we could do that. I have here a simple start where I am getting the name and experience column from the characters table. Now let us focus on the first half of the problem. Find characters who have more experience than the least experienced character. Now, because this is a toy dataset, I can sort of eyeball it. So I can scroll down here and I can see that the lowest value of experience is Pippin with 2100. And so what I need to do now is to filter out from this table all the rows that have this level of experience. But apart from eyeballing, how would we find the lowest level of experience in our data? If you thought of aggregate functions, you are right. So we have seen in a previous lecture that we have aggregated functions that take any number of values and spit out a single value that's a summary. For example, minimum and maximum. And indeed, we need to use a function like that for this problem. So your first instinct might be, let us take this table and let us filter out rows in this way. So let's say where experience is bigger than the minimum of experience. And on the surface, this makes sense, right? I am using an aggregation to get the smallest value of experience, and then I'm only keeping rows that have a higher value than that. However, as you see from this red line, this actually does not work because it tells us aggregate function is not allowed in the where clause. So what is going on here? So if you followed the lecture on aggregation, you might have a clue as to why this doesn't work, but it is good to go back to it and understand exactly what the problem is. So I'm going back to my Google Sheet over here where I have the exact same data, and I copied our current query down here. And now let's see what happens when SQL tries to run this. So SQL goes to the fantasy characters table, and the second step in the logical order, as you remember, is to filter it. And for the filter, it has to take the column of experience. So let me take this column and copy it down here. And then it has to compute minimum of experience, right? So I will define this column here, and I will use Google Sheets function to achieve that result. So equals min, and then selecting the numbers. And here I get the minimum value of experience. And now SQL has to compare these columns, but this comparison doesn't work, right? Because these are two columns that have a different number of rows. They have a different number of values. So SQL is not able to do this comparison. You cannot do an element by element comparison between a column that has 15 values and a column that has a single value. So SQL throws an error. But you might say, wait, there is a simple solution to this. Just take this value and copy it all over here until you have two columns of the same size, and then you can do the comparison. Indeed, that would work, that's a solution, but SQL doesn't do it automatically. Whereas if you work with other analytics tools such as Pandas in Python or NumPy, you will find that in a situation like this would be done automatically. This value would be copied all over here. And there's a process called broadcasting for that. But SQL does not take so many assumptions and so many risks with your data. If it literally doesn't work, then SQL will not do it. So hopefully now you have a better understanding of why this solution does not work. So how could we actually approach this problem? Now, a key insight is that I can run a different query. So I will open this on the right to find out the minimum experience, right? I can go back to the characters table and I can select the minimum of experience. This is simply what we've learned to do in the lecture on aggregations. And I get the value here that is the minimum value of experience. Now that I know the minimum value of experience, I could simply copy this value and insert it here into a where filter. And if I run this, this will actually work. It will solve my problem. The issue, of course, is that I do not want to hard code this value. First of all, it is not very practical to run a separate query and copy paste the value in the code. And second, the minimum value might change someday, and then I might not remember to update it in my code, and then this whole query would become invalid. To solve this problem, I will use a subquery, and I will simply delete the hard-coded value, and I will open round brackets, which is a way to get started on a subquery. And I will take the query that I have over here and put it in the round brackets. And when I run this, I get the result that I need. So what exactly is going on here? We are using a subquery, or in other words, a query within a query. So when SQL looks at this code, it says, all right, so this is the outer query, right? And it has a inner query inside it, a nested query. So I have to start with the innermost query. I have to start with the nested query. So let me compute this. And so SQL runs this query first, and then it gets a value out of it, which in our case, we know that is 2100. And after that, SQL substitutes this code over here by the value that was computed, and we know from before that this works as expected. And to compute the other half of our problem, we want our character to have less experience than the most experienced character. So this is just another condition in the where filter. And so I can add an and here and copy this code over here, except that now I want my experience to be smaller than the maximum of experience in my table. Now, you might know this trick that if you select only part of your code like this and then you click run, SQL will only execute that part of the code. And so here we get the actual maximum for our experience and we can write it here in the comment. And now we know that when SQL runs this query, all of this will be computed to 15,000 and then experience will be compared on that and the query will work as intended. And here is the solution to our problem. Now here's a second problem which shows another side of subqueries. We want to find the difference between a character's experience and their mentors. So let us solve it manually for one case in the characters table. So let us look at this character over here, which is Saruman with ID 11, and their experience is 8500. And then Saruman has character ID 6 as their mentor. So if I look for ID 6, we have Gandalf. This is not very canon compared to the story, but let's just roll with it. And Gandalf has 10,000 of experience. And now if we select the experience of Gandalf minus the experience of Saruman, we can see that there is a 1500 difference between their experience. And this is what I want to find with my query. Now back to my query, I will first alias my columns in order to make them more informative. And this is a great trick to make problems clearer in your head. Assign the right names to things. So here, instead of ID, I will call this Mentee ID. And here I have Mentor ID. And here, instead of experience, I will call this Mentee experience. So I have just renamed my columns. Now, the missing piece of the puzzle is the mentor experience, right? So how can I get the mentor experience? For example, in the first case, I know that character 11 is mentored by character 6. How can I get the experience of character 6? Now, of course, I can take a new tab over here, split it to the right, go to fantasy characters, filter for ID being equal to 6, which is the ID of our mentor, and get their experience. And the experience in this case is 10,000. This is the same example that we saw before. But now I would have to write this separate query for each of my rows. So here 6 I've already checked, but then I will need to check 2 and 7 and 1, and this is really not feasible, right? And the solution, of course, is to solve it with a subquery. So what I'm gonna do here is open round brackets, and in here I will write the code that I need. And here I can simply copy the code that I've written here, get experience from the characters where ID equals 6. Now, the 6 part is still hard-coded because in the first row, mentor ID is 6. To avoid hard-coding this part, there are two components to this. The first one is noticing that I am referencing the same table, fantasy.characters, in two different places in my code. And this could get buggy and this could get confusing. And the solution is to give separate names to these two instances. Now, what are the right names to give? So if we look at this outer query right here, this is really information about the mentee, right? Because we have the mentee ID, the ID of their mentor, and the mentee experience. So I can simply call this mentee table. And as you can see, I can alias my table by simply writing it like this, or I could also add the as keyword. It would work just the same. On the other hand, this table will give us the experience of the mentor. This is really information about the mentor, so we can call this mentor table. Now, we're not going to get confused anymore because these two instances have different names. And now, what do we want this ID to be if we're not going to hard code it? We want it to be this value over here. We want it to be the mentor ID value from the mentee table. We want it to be the mentee's mentor. And to refer to that column, I will get the table name dot the column name. So this is telling me get the mentor ID value from mentee table. And now that I have the subquery, which defines a column with these two brackets, I can alias the result just like I always do and run this. And now you will see, after making some room here, that we have successfully retrieved the experience value for the mentor. Now I realize that this is not the simplest process, so let us go back to our query over here and make sure that we understand exactly what is happening. Now, first of all, we're going to the characters table, which contains information about our mentee, the person who is being mentored. And we label the table so that we remember what it's about. We filter it because we're not interested in characters that do not have a mentor. And then we're getting a few data, right? The ID, in this case, represents the ID of the mentee. And we also have their mentor ID. And we also have the experience, which again, this is the table about the mentee, represents the mentee experience. Now, our goal is to also get the experience of their mentor. Our goal is to see that we have a mentor ID 6 and we want to know that their experience is 10,000. And we do that with a subquery. It's a query within a query. And in this subquery, which is an independent piece of SQL code, we are going back to the characters table, but this is another instance of the table, right, that we're looking at. So to make sure we remember that, we call this mentor table because it contains information about the mentor. And how do we make sure that we get the right value over here, that we don't get confused between separate mentors? We make sure that for each row, the ID of the character in this table is equal to the mentor ID value in the mentee table. In other words, we make sure that we plug in this value over here, in this case 6, into the table to get the right row. And then from that row, we get the experience value. All of this code over here defines a new column, which we call mentor experience. And this is basically the same thing that we did manually when we opened a table on the right and queried the table and copy pasted the hard-coded value. This is just the way to do it dynamically with a subquery. Now we are not fully done with the problem, right? Because we wanted to see the difference between the characters' experience and their mentors. So let's see how to do this. And the way to do it is with a column calculation, just like the ones we've seen before. So given that this column represents the mentor experience, I can remove the alias over here and over here as well. And I can subtract the experience from this. And a column minus a column gives me another column, which I can then alias as experience difference. And if I run this, I will see the value that we originally computed manually, which is the difference between the mentor and the mentee's experience. There's nothing really new about this, as long as you realize that this expression over here defines a column, and this is the reference to a column, and so you can subtract them and then give a name, an alias, to the result. And now we can look at our two examples of nested queries side by side, and we can figure out what they have in common and where do they differ. So what they have in common is that they're both problems that you cannot resolve with a simple query, because you need to use values that you have to compute separately, values that you cannot simply refer to by name like we usually do with our columns. In this case, on the left, you need to know what are the minimum and maximum values for experience. And in this case, on the right, you need to know what is the experience of a character's mentor. And so we solve that problem by writing a new query, a nested query, and making sure that SQL solves this query first, gets the result, and then plugs that result back into the original query to get the data we need. There is, however, a subtle difference between these two queries that turns out to be pretty important in practice. And I can give you a clue to what this difference is by telling you that on the right we have something that's called a correlated subquery, and on the left we define this as uncorrelated subquery. Now, what does this really mean? It means that here on the left, our subqueries are computing the minimum and the maximum experience, and these are actually fixed values for all of our characters. It doesn't matter which character you're looking at, the whole dataset has the same values from minimum experience and maximum experience. So you could even imagine computing these values first before running your queries. For example, you could say minimum experience is the minimum and maximum experience is the max, and then you could imagine replacing these values over here, right? This will not actually work because you cannot define variables like this in SQL, but on a logical level, you can imagine doing this, right? Because you only need to compute these two once. I will revert this here so we don't get confused. On the other hand, on the right, you will see that the value that is returned by this subquery needs to be computed dynamically for every row. This value, as you also see in the results, is different for every row because every row references a different mentor ID. And so SQL cannot compute this one value here for all rows at once. It has to recompute it for every row. And this is why we call it a correlated subquery, because it's connected to the value that is in each row, and so it must run for each row. And an important reason to distinguish between uncorrelated and correlated subqueries is that you can imagine that correlated subqueries are actually slower and more expensive to run because you're running a SQL query for every row, at least at the logical level. So this was our introduction to subqueries. They allow you to implement more complex logic, and as long as you understand it logically, you're off to a great start. And then by doing exercises and solving problems, you will learn with experience when it's the case to use them. In the last lecture, we saw that we could use subqueries to retrieve singular values. For example, what is the minimum value of experience in my dataset? But we can also use subqueries and common table expressions as well to create new tables altogether. So here's a motivating example for that. So what I'm doing in this query right here is that I am scaling the value of level based on the character's class. And you might need this in order to create some balance in your game or for whatever reason. Now, what this does is that if the character is mage, the level gets divided by half or multiplied by 0.5. If the character is archer or warrior, the level, we take the 75% of it, and in all other cases, the level gains 50%. So the details are not very important, it's just an example, but the point is that we modify the value of level based on the character class, and we do this with the case when statement that we saw in a previous lecture. And as you can see in the results, we get a new value of power level for each character that you can see here. But now, let's say that I wanted to filter my characters based on this new column of power level. Say that I wanted to only keep characters that have a power level of at least 15. How would I do that? Well, we know that the where filter can be used to filter rows, so you might just want to go here and add a where statement and say where power level is equal or bigger than 15. But this is not going to work, right? We know this cannot work because we know how the logical order of SQL operations works. And so the case when column that we create, power level, is defined here at the select stage. But the where filter occurs here at the beginning, right after we source our table. So due to our rules, the where component cannot know about this power level column that will actually get created later. So the query that we just wrote actually violates the logical order of SQL operations, and this is why we cannot filter here. Now, there is actually one thing that I could do here to avoid using a subquery and get around this error. And that something would be to avoid using this alias power level that we assign here and that the where statement cannot know about, and replace it with the whole logic of the case when statement. So this is gonna look pretty ugly, but I'm going to do it. And if I run this, you will see that we in fact get the result we wanted. Now, in the where lecture, we saw that the where clause doesn't just accept simple logical statements. You can use all the calculations and all the techniques that are available to you at the select stage. And you can also use case when statements. And this is why this solution here actually works. However, this is obviously very ugly and impractical, and you should never duplicate code like this. So I'm going to remove this where clause over here and show you how you can achieve the same result with a subquery. So let me first rerun this query over here so that you can see the results. And now what I'm going to do, I'm going to select this whole logic over here and wrap it in round brackets. And then up here, I'm going to say select star from. And when I run this new query, this data that I'm seeing over here should be unchanged. So let us run it. And you will see that the data has not changed at all. But what is actually happening here? Well, it's pretty simple. Usually we say select star from fantasy characters, right? And by this, we indicate the name of a table that our system can access. But now, instead of a table name, we are showing a subquery. And this subquery is a piece of SQL logic that obviously returns a table. So SQL will look at this whole code and will say, okay, there is a outer query, which is this one, and there is an inner query, a nested query, which is this one. So I will compute this one first, and then I will treat this as just another table that I can then select from. And now, because this is just another table, we can actually apply a where filter on top of it. We can say where power level is equal or greater than 15, and you will see that we get the result we wanted, just like before. But now our code looks actually better and the case when logic is not duplicated. If you wanted to visualize this in our schema, it would look something like this. So the flow of data is the following. First, we run the inner query that works just like all the other queries we've seen until now. It starts with the from component, which gets the table from the database, and then it goes through the usual pipeline of SQL logic that eventually produces a result, which is a table. Next, that table gets piped into the outer query. The outer query also starts with the from component, but now the from component is not reading directly from the database, it is reading the result of the inner query. And now the outer query goes through the usual pipeline of components, and finally it produces a table, and that table is our result. And this process could have many levels of nesting because the inner query could reference another query which references another query, and eventually we would get to the database, but it could take many steps to get there. And to demonstrate how multiple levels of nesting works, I will go back to my query over here and I will go into my inner query, which is this one, and this is clearly referencing the table in the database, but now instead of referencing the table, I will reference yet another subquery, which can be something like from fantasy characters, where is alive equals true, select star. So I will now run this and we have added yet another subquery to our code. This was actually not necessary at all. You could add the where filter up here, but it is just to demonstrate the fact that you can nest a lot of queries within each other. The other reason I wanted to show you this code is that I hope you will recognize that this is also not a great way of writing code. It can get quite confusing and it is not something that can be easily read and understood. One major issue is that it interrupts the natural flow of reading code because you constantly have to interrupt a query because another nested query is beginning within it. So you will read select star from, and then here another query starts, and this is also querying from another subquery, and after reading all of these lines you will find this where filter that actually refers to the outer query that has started many lines back. And if you find this confusing, well, I think you're right, because it is. And the truth is that when you read code on the job or in the wild, or when you see solutions that people propose to coding challenges, unfortunately this is something that occurs a lot. You have subqueries within subqueries within subqueries, and very quickly the code becomes impossible to read. Fortunately, there is a better way to handle this, and a way that I definitely recommend over this, which is to use common table expressions, which we shall see shortly. It is, however, very important that you understand this way of writing subqueries and that you familiarize yourself with it, because whether we like it or not, a lot of code out there is written like this. We've seen that we can use the subquery functionality to define a new table on the fly just by writing some code. A new table that we can then query just like any other SQL table. And what this allows us to do is to run jobs that are too complex for a single query. And to do that without defining new tables in our database and storing new tables in our database. It is essentially a tool to manage complexity, and this is how it works for subqueries. So instead of saying from and then the name of a table, we open round brackets and then we write a independent SQL query in there. And we know that every SQL query returns a table, and this is the table that we can then work on. What we do here is to select star from this table and then apply a filter on this new column that we created in the subquery power level. And now I will show you another way to achieve the same result, which is through a functionality called common table expressions. To build a common table expression, I will take the logic of this query right here and I will move it up. And next, I will give a name to this table. I will call it power level table. And then all I need to say is with power level table as, followed by the logic. And now this is just another table that is available in my query. And it is defined by the logic of what occurs within the round brackets. And so I can refer to this over here and query it just like I need. And when I run this, you see that we get the same results as before. And this is how a common table expression works. You start with the keyword with, you give an alias to the table that you're going to create, you put as, open round brackets, write an independent query that will of course return a table under this alias over here, and then in your code you can query this alias just like we've done until now for any SQL table. And although our data result hasn't changed, I would argue that this is a better and more elegant way to achieve the same result, because we have separated in the code the logic for these two different tables. Instead of putting this logic in between this query and sort of breaking the flow of this table, we now have a much cleaner solution where first we define the virtual table that we will need. And by virtual, I mean that we treat it like a table, but it's not actually saved in our database. It's still defined by our code. And then below that, we have the logic that uses this virtual table. We can also have multiple common table expressions in our query. Let me show you what that looks like. So in our previous example on subquery, we added another part where here, instead of querying the fantasy characters table, we queried a filter on this characters table, and it looked like this. We were doing select star where is alive equals true. So I'm just reproducing what I did in the previous lecture on subqueries. Now you will notice that this is really not necessary, because all we're doing here is add a where filter, and we could do this in this query directly, but please bear with me because I just want to show you how to handle multiple queries. The second thing I want to tell you is, although this code actually works and you can verify for yourself, I do not recommend doing this, meaning mixing common table expressions and subqueries. It is really not advisable because it adds unnecessary complexity to your code. So here we have a common table expression that contains a subquery, and I will rather turn this into a situation where we have two common table expressions and no subqueries at all. And to do that, I will take this logic over here and paste it at the top. And I will give this now an alias. So I will call it characters alive, but you can call it whatever is best for you. And then I will do the keyword as, add some lines in here to make it more readable. And now, once we are defining multiple common table expressions, we only need to do the with keyword once at the beginning, and then we can simply add a comma, and please remember this, the comma is very important. And then we have the alias of the new table, the as keyword, and then the logic for that table. All that's needed to do now is to fill in this from, because we took away the subquery, and we need to query the characters alive virtual table here, and this is what it looks like. And if you run this, you will get your result. So this is what the syntax looks like when you have multiple common table expressions. You start with the keyword with, which you're only going to need once. And then you give the alias of your first table, as keyword, and then the logic between round brackets. And then for every extra virtual table that you want to add, for every extra common table expression, you only need to add a comma, and then another alias, the as keyword, and then the logic between round brackets. And when you are done listing your common table expressions, you will omit the comma. You will not have a comma here because it will break your code. And finally, you will run your main query. And in each of these queries that you can see here, you are totally free to query real tables, material tables that exist in your database, as well as common table expressions that you have defined in this code. And in fact, you can see that our second virtual table here is querying the first one. However, be advised that the order in which you write these common table expressions matters, because a common table expression can only reference common table expressions that came before it. It's not going to be able to see those that came after it. So if I say here, instead of from fantasy characters, I try to query from power level table, you will see that I get an error from BigQuery because it doesn't recognize it basically, because the code is below. So the order in which you write them matters. Now, an important question to ask is, when should I use subqueries and when should I use common table expressions? And the truth is that they have a basically equivalent functionality. What you can do with the subquery, you can do with a common table expression. My very opinionated advice is that every time you need to define a new table in your code, you should use a common table expression, because they are simpler, easier to understand, cleaner, and they will make your code more professional. In fact, I can tell you that in the industry, it is a best practice to use common table expressions instead of subqueries. And if I were to interview you for a data job, I would definitely pay attention to this issue. But there is an exception to this, and this is the reason why I'm showing you this query, which we wrote in a previous lecture on subqueries. This is a query where you need to get a single specific value, right? So if you remember, we wanted to get characters whose experience is above the minimum experience in the data and also below the maximum experience. So characters that are in the middle. To do this, we need to dynamically find at any point, when this query is being run, what is the minimum experience and the maximum experience. And the subquery is actually great for that. You will notice here that we don't really need to define a whole new table. We just really need to get a specific value. And this is where a subquery works well, because it implements very simple logic and doesn't actually break the flow of the query. But for something more complex like power level table, this specific query we're using here, which takes the name, takes the level, then applies a case when logic to level to create a new column called power level. You could do this with a subquery, but I actually recommend doing it with a common table expression. And this is a cool blog post on this topic by the company DBT. It talks about common table expressions in SQL, why they are so useful for writing complex SQL code, and the best practices for using common table expressions. And towards the end of the article, there's also an interesting comparison between common table expressions and subqueries. And you can see that CTE's common table expressions are more readable, whereas subqueries are less readable, especially if there are many nested ones. So, a subquery within a subquery within a subquery quickly becomes unreadable. Recursiveness is a great advantage of CTEs, although we won't examine this in detail. But basically what this means is that once you define a common table expression in your code, you can reuse it in any part of your code. You can use it in multiple parts, right? You can use it in other CTEs, you can use it in your main query, and so on. On the other hand, once you define a subquery, you can really only use it in the query in which you defined it. You cannot use it in other parts of your code, and this is another disadvantage. This is a less important factor, but when you define a CTE, you always need to give it a name, whereas subqueries can be anonymous. You can see it very well here. We of course had to give a name to both of these CTEs, but the subqueries that we're using here are anonymous. However, I wouldn't say that's a huge difference. And finally, you have that CTEs cannot be used in a where clause, whereas subqueries can. And this is exactly the example that I've shown you here. Because this is a simple value that we want to use in our where clause in order to filter our table, subqueries are the perfect use case for this, whereas CTEs are suitable for more complex use cases when you need to define entire tables. In conclusion, the article says CTEs are essentially temporary views that you can use. I've used the term virtual table, but temporary view works just as well, conveys the same idea. They are great to give your SQL more structure and readability, and they also allow reusability. Before we move on to other topics, I wanted to show you what an amazing tool common table expressions are to create complex data workflows. Because common table expressions are not just a trick to execute certain SQL queries, they're actually a tool that allows us to build data pipelines within our SQL code, and that can really give us data superpowers. So here I have drawn a typical workflow that you will see in complex SQL queries that make use of common table expressions. Now what we're looking at here is a single SQL query. It's however a complex one because it uses CTEs. And the query is represented graphically here and in a simple code reference here. The blue rectangles represent the common table expressions, these virtual tables that you can define with the CTE syntax. Whereas the red square represents the base query, the query at the bottom of your code that ultimately will return the result. So a typical flow will look like this. You will have a first common table expression called T1 that is a query that references a real table, a table that actually exists in your dataset, such as fantasy characters. And of course, this query will do some work, right? It can apply filters, it can calculate new columns, and so on, everything that we've seen until now. And then the result of this query gets piped in to another common table expression. This one is T2, that gets the result of whatever happened at T1 and then applies some further logic to it, applies some more transformations. And then again, the result gets piped into another table where more transformations run, and this can happen for any number of steps until you get to the final query. And in the base query, we finally compute the end result that will then be returned to the user. So this is effectively a data pipeline that gets data from the source and then applies a series of complex transformations. And this is similar to the logical schema that we've been seeing about SQL, right? Except that this is one level further. Because in our usual schema, the steps are done by clauses, by these components of the SQL queries. But here, every step is actually a query in itself. So of course, this is a very powerful feature. And this data pipeline applies many queries sequentially until it produces the final result. And you can do a lot with this capability. And also, you should now be able to understand how this is implemented in code. So we have our usual CTE syntax with, and then the first table we call T1, and then here we have the logic within round brackets for T1. And you can see here that in the from, we are referencing a table in the dataset. And then for every successive common table expression, we just add a comma, a new alias and the logic, comma, new alias and the logic. And finally, when we're done, we write our base query. And you can see that the base query is selecting from T3, T3 is selecting from T2, T2 is selecting from T1, and T1 is selecting from the database. But you are not limited to this type of workflow. Here is another, maybe slightly more complex workflow that you will also see in the wild. And here you can see that at the top we have two common table expressions that reference the database. So you can see here, like the first one is getting data from table 1 and then transforming it. The second one is getting data from table 2 and then transforming it. And next we have the third CTE that's actually combining data from these two tables over here. So we haven't yet seen how to combine data except through the union. I wrote the join here, which we're going to see shortly, but all you need to know is that T3 is combining data from these two parent tables. And then finally, the base query is not only using the data from T3, but also going back to T1 and using that data as well. And you remember we said that great thing about CTEs is that tables are reusable. You define them once and then you can use them anywhere. Well, here's an example with T1, because T1 is defined here at the top of the code, and then it is referenced by T3, but it is also referenced by the base query. So this is another example of a workflow that you could have, and really the limit here is your imagination and the complexity of your needs. You can have complex workflows such as this one, which can implement very complex data requirements. So this is a short overview of the power of CTEs, and I hope you're excited to learn about them and to use them in your SQL challenges. We now move on to joins, which are a powerful way to bring many different tables together and combine their information. And I'm going to start us off here with a little motivating example. Now, on the left here, I see my characters table. And by now we're familiar with this table. So let's say that I wanted to know for each character how many items they are carrying in their inventory. Now, you will notice that this information is not available in the characters table. However, this information is available in the inventory table. So how exactly does the inventory table works? When you are looking at a table for the first time and you want to understand how it works, the best question you can ask is the following. What does each row represent? So what does each row represent in this table? Well, if we look at the columns, we can see that for every row of this table, we have a specific character ID and an item ID, as well as a quantity and some other information as well, such as whether the item is equipped, when it was purchased, and so on. So looking at this, I realized that each row in this table represents a fact, the fact that a character has an item, right? So I know by looking at this table that character ID 2 has item 101 and character ID 3 has item 6 and so on. So clearly I can use this in order to answer my question. So how many items is Gandalf carrying? To find this out, I have to look up the ID of Gandalf, which as you can see here is 6. And then I have to go to the inventory table and in the character ID column, look for the ID of Gandalf, right? Now, unfortunately, it's not ordered, but I can look for myself here and I can see that at least this row is related to Gandalf because he has character ID 6. And I can see that Gandalf has item ID 16 in his inventory. And I'm actually seeing another one now, which is this one, which is 11. And I'm not seeing any other item at the moment. So for now, based on my imperfect visual analysis, I can say that Gandalf has 2 items in his inventory. Of course, our analysis skills are not limited to eyeballing stuff, right? We have learned that we can search a table for the information we need. So I could go here and query the inventory table in a new tab, right? And I could say, give me from the inventory table where character ID equals 6. This should give me all the information for Gandalf. And I could say, give me all the columns. And when I run this, I should see that indeed we have 2 rows here and we know that Gandalf has items 16 and 11 in his inventory. We don't know exactly what these items are, but we know that he's carrying 2 items. So that's a good start. Okay, but what if I wanted to know which items Frodo is carrying? Well, again, I can go to the characters table and look up the name Frodo, and I find out that Frodo is ID 4. So going here, I can just plug that number into my where filter, and I will find out that Frodo is carrying a single type of item, which has ID 9, although it's in a quantity of 2. And of course, I could go on and do this for every character, but it is quite impractical to change the filter every time. And what if I wanted to know how many items each character is carrying, or at least which items each character is carrying, all at once? Well, this is where joins come into play. What I really want to do in this case is to combine these 2 tables into one, and by bringing them together to create a new table which will have all of the information that I need. So let's see how to do this. Now, the first question we must answer is, what unites these 2 tables? What connects them? What can we use in order to combine them? And actually, we've already seen this in our example. The inventory table has a character ID field, which is actually referring to the ID of the character in the characters table. So we have 2 columns here, the character ID column in inventory and the ID column in characters. which actually represent the same thing, the identifier for a character. And this logical connection, the fact that these columns represent the same thing, can be used in order to combine these tables. So let me start a fresh query over here. And as usual, I will start with the from part. Now, where do I want to get my data from? I want to get my data from the characters table, just as we've been doing until now. However, the characters table is not enough for me anymore. I need to join this table on the fantasy.inventory table. So I want to join these two tables. How do I want to join these two tables? Well, we know that the inventory table has a character ID column, which is the same as the characters table's ID column. So like we said before, these two columns from the different tables, they represent the same thing. So there's a logical connection between them, and we will use it for the join. And I want to draw your attention to the notation that we're using here, because in this query, we have two tables present. And so it is not enough to simply write the name of columns. It is also necessary to specify to which table each column belongs. And we do it with this notation. So the inventory.character is saying that we are talking about the character ID column in the inventory table and the ID column in the characters table. So it's important to write columns with this notation in order to avoid ambiguity when you have more than one table in your query. So until now, we have used the from clause to specify where do we want to get data from. And normally this was simply specifying the name of a table. Here we are doing something very similar, except that we are creating a new table that is obtained by combining two pre-existing tables. Okay, so we are not getting our data from the characters table, and we are not getting it from the inventory table, but we are getting it from a brand new table that we have created by combining these two. And this is where our data lives. And to complete the query for now, we can simply add a select star, and you will now see the result of this query. So let me actually make some room here and expand these results so I can show you what we got. And as you can see here, we have a brand new table in our result. And you will notice, if you check the columns, that this table includes all of the columns from the characters table and also all of the columns from the inventory table, as you can see here. And they have been combined by our join statement. Now, to get a better sense of what's happening, let us get rid of this star and let us actually select the columns that we're interested in. And once again, I will write columns with this notation in order to avoid ambiguity. And in selecting these columns, I will remind you that we have all of the columns from the characters table and all of the columns from the inventory table to choose from. So what I will do here is that I will take the ID columns from characters, and I will take the name column from characters. And then I will want to see the ID of the item. So I will take the inventory table and the item ID column from that table. And from the inventory table, I will also want to see the quantity of each item. And to make our results clearer, I will order my results by the character's ID and the item ID. And you can see here that we get the result that we needed. We have all of our characters here with their IDs and their name. And then for each character, we can tell which items are in their inventory. So you can see here that Aragorn has item ID 4 in his inventory in quantity of 2. He also has item 99. So because of this, Aragorn has 2 rows. If we look back at Frodo, we see the information that we retrieved before, and the same for Gandalf, who has these 2 items. So we have combined the characters table and the inventory table to get the information that we needed. What does each row represent in our result? Well, it's the same as the inventory table. Each row is a fact, which is that a certain character possesses a certain item. But unlike the inventory table, we now have all the information we want for a character and not just the ID. So here we're showing the name of each character, but we could of course select more columns and get more information for each character as needed. Now a short note on notation. When you see SQL code in the wild and a query is joining on 2 or more tables, people, programmers were usually quite lazy and we don't feel like writing the name of the table all of the time, right? Like we were doing in this case with characters. So what we usually do is that we add an alias on the table like this. So from fantasy characters, call it C, we will join on inventory, call it I, and then basically we use this alias everywhere in the query, both in the instructions for joining and in the column names, and the same with characters. So I will substitute everything here. And yes, maybe it's a bit less readable, but it's faster to write and we programmers are quite lazy, so you'll often see this notation. And you will often also see that in the code we omit the as keyword, which can be, let's say, implicit in SQL code. And so we write it like this: from fantasy.character C, join fantasy.inventory I, and then C and I refer to the 2 tables that we're joining. And I can run this and show you that the query works just as well. Now, we've seen why join is useful and how it looks like, but now I want you to get a detailed understanding of how exactly the logic of join works. And for this, I'm gonna go back to my spreadsheet, and what I have here is my characters table and my inventory table. These are just like you've seen them in BigQuery, except that I'm only taking 4 rows each in order to make it simpler for the example. And what you see here is the same query that I've just run on BigQuery. This is a query that takes the characters table, joins it on the inventory table on this particular condition, and then picks a few columns from this. So let us see how to simulate this query in Google Sheets. Now, the first thing I need to do is to build the table that I will run my query on. Because as we've said before, the from part is now referencing not the characters table, not the inventory table, but the new table, which is built by combining these 2. And so our first job is to build this new table. And the first step to building this new table is to take all of the columns from characters and put them in the new table. And then take all of the columns from inventory and then put them in the new table. And what we've obtained here is the structure of our new table. The structure of our new table is simply created by taking all of the columns of the table on the left along with all of the columns from the table on the right. Now, I will go through each character in turn and consider the join condition. The join condition is that the ID of a character is present in the character ID column of inventory. So let us look at my first character. We have Aragorn and he has ID 1. Now, is this ID present in the character ID column? Yes, I see it here in the first row. So we have a match. Given that we have a match, I will take all of the data that I have in the characters table for Aragorn, and then I will take all of the data in the inventory table for the row that matches. And I have built here my first row. Do I have any other row in the inventory table that matches? Yes, the second row also has a character ID of 1. So because I have another match, I will repeat the operation. I will take all of the data that I have in the left table for Aragorn, and I will add all of the data from the right column in the row that matches. Now, there are no more matches for ID 1 in the inventory table, so I can proceed. And I will proceed with Legolas. He has character ID of 2. Question: is there any row that has the value 2 in the character ID column? Yes, I can see it here. So I have another match. So just like before, I will take the information for Legolas and paste it here. And then I will take the matching row, which is this one, and paste it here. We move on to Gimli because there's no other matches for Legolas. Now, Gimli has ID 3 and I can see a match over here. So I will take the row for Gimli, paste it here, and then take the matching row, character ID 3, and paste it here. Great. Finally, we come to Frodo, character ID 4. Is there any match for this character? I can actually find no match at all. So I do nothing. This row does not come into the resulting table because there is no match. And this completes the job of this part of the query over here, building the table that comes from joining these two tables. This is my resulting table. And now to complete the query, I simply have to pick the columns that the query asks for. So the first column is character.id, which is this column over here. So I will take it and I will put it in my result. The second column I want is character.name, which is this column over here. The third column is the item ID column, which is this one right here. And finally, I have quantity, which is this one right here. And this is the final result of my query. And of course, this is just like any other SQL table, so I can use all of the other things I've learned to run logic on this table. For example, I might only want to keep items that are present in a quantity of 2. And so to do that, I will simply add a where filter here, and I will refer the inventory table because that's the parent table of the quantity column. So I will say I.quantity bigger or equal to 2. And then how my query will work is that first it will build this table like we've seen. So it will do this stage first. And then it will run the where filter on this table, and it will only keep the rows where quantity is at least 2. And so as a result, we will only get this row over here instead of this result that we see right here. Except that we will of course also have to only keep the columns that are specified in the select statement. So we will get ID, name, item ID, and quantity. So this will be the result of my query after I've added a where filter. So let us actually take this and add it to BigQuery and make sure that it works. So I have to add that after the from part and before the order by part, right? This is the order. And after I run this, I will see that indeed I get Aragorn and Frodo. Is not exactly the same as in our sheet, but that's because our sheet has less data. But this is what we want to achieve. And now let us go back to our super important diagram of the order of SQL operation, and let us ask ourselves, where does the join fit in this schema? And as you can see, I have placed join at the very beginning of our flow together with the from, because the truth is that the join clause is not really separate from the from clause. They are actually one and the same component in the logical order of operations. So as you remember, the first stage specifies where our data lives, where do we want to get our data from. And until now, we were content to answer this question with a single table name, with the address of a single table, because all the data we needed was in just one table. And now, instead of doing this, we are taking it a step further. We are saying our data lives in a particular combination of 2 or more tables. So let me tell you which tables I want to combine and how I want to combine them. And the result of this will be, of course, yet another table. And then this table will be the beginning of my flow. And after that, I can apply all the other operations that I've come to know on my table, and it will work just like all our previous examples. The result of a join is, of course, just another table. So when you look at a SQL query and this query includes a join, you really have to see it as one and the same with the from part. It defines the source of your data by combining tables, and everything else that you do will be applied not to a single table, not to any of the tables that you're combining. Everything that you do will be applied to the resultant table that comes from this combination. And this is why from and join are really the same component, and this is why they are the first step in the logical order of SQL operations. Let us now briefly look at multiple joins, because sometimes the data that you need is in 3 tables or 4 tables, and you can actually join as many tables as you want, or at least as many tables as your system allows you to join before it becomes too slow. So we have our example here from before. We have each character and we have their name, and we know which items are in their inventory, but we actually don't know what the items are. We just know their ID. So how can I know that if Aragorn has item 4, what item does Aragorn actually have? What is the name of this item? Now, obviously this information is available in the items table that you have here on the right, and you can see here that we have a name column. And just like before, I can actually eyeball it, I can look for it myself. I know that I'm looking for item ID 4, and if I go here and I go to 4, I can see that this item is a healing potion. And now let us see how we can add this with the join. So now I will go to my query, and after joining with characters and inventory, I will take that result and simply join it on a third table. So I will write join on fantasy.items, and I can call this IT to use a brief form because I am lazy, as all programmers are. And now I need to specify the condition on which to join. So the condition is that the item ID column, which actually came from the inventory table, right? That's its parent. So I'm going to call it inventory.item ID, except that, yeah, I'm referring to inventory as a simple I. That is the brief form, is the same as the items table, the ID column in the items table. And now that I've added my condition,